Hi, my name is Fadi Al-Jaljouli. I am a PhD student in the modeling team in the IAK1 in Forschungszentrum Jülich. Today I'm going to talk about my topic, which is the stability of all solid-state lithium-ion batteries. I would like to start with a little bit introduction here. First of all, lithium-ion batteries is taking a huge role in our life. It's go in a lot of electronic devices in our recent life. The requirements of the recent or in the storage batteries are: first, that it should be easy to use; second, it should be reliable; and don't forget to have a good electricity capacity. It should be also friendly to the environment, and the most important thing is to be safe. And this is the key point here. In the storage industry, two things have been to develop. First, we either develop the recent battery we have, or we need to find out or to create out a new batteries. This is why we first need to talk about the traditional lithium-ion batteries. The traditional lithium-ion batteries consist of, first, the cathode. The cathode here, it consists of the lithium cobalt oxide, for short, it's LCO. As you can see, it has a layered structure. It facilitates the diffusion of the ions between the different electrodes. So the lithium ions are stored in between them, while the electrons are stored just to balance the charge. The second part is the anode. The anode is just a graphite. It's just a material that you use in your pencil, for example. It has no effect, no work, no rule in your electrochemical reaction, but it just stores the lithium ions in its layer. The third parameter is the electrolyte. You know, it's very important that the lithium-ion batteries, the lithium ions, don't touch between the electrodes, between the cathode and the anode. That's why we need a separator that allow the ions to flow between them, but to prevent the electrons. The fourth parts are the current collectors, where we are using the copper for the anode and the aluminum for the cathode. But imagine that in such cases with the traditional lithium-ion batteries, where we have liquid or gel electrolyte, if it's evaporized, then it's going to touch between the electrodes, will cause an explode, as we saw, and the result will be dangerous, something like this. So we will move on to the all solid-state lithium-ion batteries. In this case, we are not talking anymore about the electrolyte. We are talking about thin layer, which is called a separator, and there will be no more just an LCO, lithium cobalt oxide, in the cathode, because lithium cobalt oxide in this case is not immersed with the electrolyte, so there will be no transportation of the ions between the cathode to the anode. That's why we need to make a composite material, which means that the cathode and the electrolyte should be together. In this case, we are enhancing the ionic conductivity and also keeping the electrical conductivity. So, what's the problem with lithium cobalt oxide is during the delithiation, there is a change in the lattice structure from the hexagonal phase to the monochromic shape, which means that there will be a change in the volume expansion. It will expand more in the C direction. This will cause a stress, and we are going to see that later. Now, in all solid-state lithium-ion batteries, what we have is there is no space between the material, between the particles. That means when the expansion is happening, there will be a developing in a stress. This stress developing will cause a fatigue or degradation. Look at this microstructure here. We have a cycled and centered material, which consists of lithium cobalt oxide, as you can see, in the dark place, and LLZ in a bright place, and the pores as a black. But if we zoom it very well, you can see cracks over there in the lithium cobalt oxide. This will be solved. So as a brief, and due to the lithium concentration, we have a lattice change, and then this yields us to a volume change in the C direction especially, and this will generate a stress, and after that, this will create a fracture or degradation. This degradation we can see here as in TEM images, TEM images in lithium cobalt oxide, but we see it very often in the foot of elephants. So, what is our work plan? Our work plan here is first to study the microstructural parameters design, which means the grain size of the LCO and LLZ, the phase ratio, and the relative density. Now, after that, we are going to characterize the microstructural characterization, which means we will focus more on the interface area between LCO and LLZ, because we believe that more area between LCO and LLZ will give us more stress. Finally, we will characterize the electrode itself in terms of the mechanical properties and the electrical properties. The goal is to minimize the stress while keeping the electrical and ionic conductivity and the capacity. But hold on, we need also to investigate about the factor that govern this stress in the design, on the microstructure. So the first step is to get these images taken by FIP, okay, slice it, and then after some binarization and some graphical design, we have this regenerated microstructure using a simulation called Geodict. After that, we will build our own microstructure to mimic it, first by biling, as you can see here, in the Z direction. So the particles are falling down from the Z direction. The result will be like this. After that, we can see an empty spaces. We don't like it at all because it's not representative. That's why we are going to crop it. And after that, the final step is to center. And when we are talking about centering, who know nothing about it, it's just like baking a cake. So after finishing this, we are going to make a mechanical stress calculations. But we know this scenario. The scenario is when we have a stress-free after processing, we have also and after delithiation, we know that LCO from the literatures, we know that the LCO will have a high compressive force, while the LZ have a very high tensile stress. So when we see this cross-sectional distribution area, we can see that we are going to use these parameters, the elastic modulus of LCO, the elastic modulus of LLZ, and the percentage of volume expansion of the LCO, which is 4%. But we are going to characterize this in two terms. The first term is isotropic, where all the material are expanded in the all directions, and anisotropic, which is only expanded in one direction only. It looks like a balloon when you blow it sometimes. So we generated what we had done yet. We had generated two types of microstructure. The first microstructure is rounded shape microstructure, where only two particles, two shapes used, which are the polyhedron for LCO and spheres, of course, and the spherical LLZ. And the second microstructure, or the second shape, is the LLZ fiber, and we use here spherical shape of LCO, while fibers LLZ. And then after that, we have some results. Regarding to the fiber LLZ, the shape, the grain size of the fibers has no effect at all on the stress. And when we talk about the grain size, we are talking about the diameter of the LCO, the diameter of the LLZ, and the LLZ length. While when we again about the fiber LLZ, when we investigated the relative density, we saw that the stress is increasing as we increase the relative density. Finally, regarding to the fiber, to the LLZ fiber, we concern about the orientation. So we created 4 microstructures with different orientations from 0 degree, 45 degree, 90 degree, and 135 degree, when we saw that when we have aligned microstructure, we have less stress than the random shape fiber LLZ. And finally, when we talk about the rounded shape microstructure, what we know so far is when we increase the relative density, we also increase the stress. It's familiar with the fiber LLZ too. But when we compare the fiber shape with rounded shape microstructures, we saw that in case of isotropic, we have 28% less in fiber LLZ in terms of a stress of LLZ, but we have around 17% of LCO stress. So the fiber LLZ is lower than the rounded shape in case of isotropic, but for the anisotropic case, it was 49% for LLZ, while it was just 20% for LCO. So, as a conclusion, all solid state batteries are is better than traditional battery, lithium ion batteries in terms of functionality and safety. The second is the relative density plays a great role in increasing the stress in both LCO and LLZ. The fiber orientation also have a rule on increasing the stress in the microstructure. And finally, when the structure where LLZ fiber used is less than the rounded shape one. Our outlook is to have a physical explanation of the previous parameters. The second, and also investigate the effect of LCO, solid volume fraction, on the stresses. And we also would like to investigate the effect of these parameters, the previous parameters, on the conductivity. And when we are to talk about conductivity, we are talking about both ionic and electronic. Finally, we need to study the thermocouple stress on during the sintering process. Thank you very much.